And I'm going to say so far the performance has been excellent. I begin to, have a lot of confidence with this class. So it means you are really getting the information. But if there's anyone who's struggling, please make sure you visit with me during my office hour. You don't need to, I don't hold office hour in person. You can join Zoom. It's going to be the same class, the same as the Zoom that we use in class. Now I want to welcome you to sampling distribution of proportions. Okay. In the sampling distribution, we're going to talk about some continuous distribution. We're going to look at the example. Now, if you take a look at what we did last time, we actually talked about sampling distribution of mean, right? Where mean become random variable. How can mean become random variable? When you go into population several times, you get different values for mean, right? You get x bar 1, okay? X bar 1, X bar 2, up to X bar n. And in a situation where this become a random variable, then you now need to look at the distribution for that, okay? And we say, okay, the distribution, if the distribution is normal, we say that X bar will follow normal with means and sigma square n, where what we're trying to say, expected value of X bar is mu, the variance of X bar is sigma squared over n, then the standard deviation of X bar is basically going to be sigma over root n. This is like talking about the sampling distribution of mean. But let me tell you this. When we are investigating, okay, we normally investigate, there are two common parameters that we normally investigate, two common parameters. When I say parameter, in the last class, I said parameter is any population characteristic value that we seek to determine that, just like anything that we want to know. What are the things we want to know? What we want to know mu. We want to know proportion. Okay, this is what we call population mean. Okay, population mean. This is what we call population proportion. Now, the last time, we believe that when we can study the entire elements in the population, we're going to take a sample. But when we visit the population several times, we get several means. Okay? And because of that, because mean becomes random variable, we need to get the probability distribution of that. We expect the probability distribution to be normal. But what are we going to do if it is not? If I'm choosing from a population that is normal, okay, I can choose whatever sample size because the population is already normal. The sampling distribution of the mean from such population will be normal. But if I'm choosing from a population that is not normal, then the central limit theorem needs to apply, which means my sample size have to be at least 30 before the sampling distribution of this guy will be normal. Now, we're no longer focusing on this guy now. Today, we want to focus on proportion. And the example is going to be, if I really want to know how many Americans approve the job the president is doing, okay, and I ask all of you to conduct the research. I want you guys to go into American population, and maybe I ask you to take a sample size of 50 each and every one of you. At the end of the day, are you going to get the same result? Is your result going to be the same? I'm asking question. Is it going to be the same? No, because the people you choose is different from people you choose. You guys are choosing at random, right? So which means even though what we're looking for this guy, we're looking for the population proportion, a true value of proportion, okay, the proportion of Americans who approve the job the president is doing. Now, if you go into the population, let's say you get a pick up 1, that's a sample proportion. Another person go pick up 2, pick up 3, until you get a pick up n. Look at that. And what is pick up? The pick up, it means estimate of the population proportion. Pick up, that is estimate of the population proportion. Don't forget, what we need is a population proportion. But we don't have resources to go into American population to study everybody. We're going to take a sample. When you take a sample, let's say you take a sample of n, size n, how many out of your sample n, how many approve? How many of them that approve the job the president is doing? That's going to be X. Okay, X over n. So if each and every one of you should go into American population, you're actually going to have a different result, even though you are taking the same sample size. Does that make sense? Therefore, your result varies. When your result varies, it becomes a random variable. Does that make sense? And if your result becomes a random variable, okay, if you take a look at what I'm projecting now, this is a typical. If X in your sample, if X say, okay, we support the job the president is doing, n minus S, we say, no, the president is not doing great. What have you done? You partition your sample into 2 groups. If the first group are those ones that approve the job the president is doing, because when you ask them a question, it's a yes or no. Oh, do you approve the job the president is doing? Yes, no, yes, no. That X will be the number of people who say yes. N minus S will be the number of people who say no. Does that make sense? And you know what you're looking for? In the general population, okay, you also want to partition the general population into 2. Those who approve and those who do not approve. But you do not have the resources to study everybody in the population. That was why you choose a sample size. Any question about, you can say a P cap? The P cap means sample proportion. The P without a cap is a population proportion. That is what we're looking for. But we believe that the P with a cap will represent the one without a cap. Now, my X that I just talked about will follow binomial distribution. Why? Because how many possible outcomes? 2. How many possible outcomes? 2. And your numbers of trial is more than 1. You know that, right? If you take a sample more than 1, when you go into American population, right? You're only going to take, can you investigate 1 person? Is it possible you investigate just 1 person? No, we don't do that. You're going to investigate more than 1 person. And in each stage of your investigation, the outcome is dichotomous. You're actually going to have 2 possible outcomes for every individual you investigate. Okay? It's going to be, oh, yes, I approve the job the president is doing. Or, no, I did not approve the job the president is doing. Does that make sense to everyone now? Okay, now it follows binomial. And don't forget, if X follow binomial, what is the average? Expected value of X is going to be NP. Do you remember? We've done that last week. The variance of X is going to be NPQ. But let me tell you now, we now want to have a new variable, which is no longer going to be X, but it's going to be a P cap. You know why? It's a P cap. Because when you guys go into the population now to investigate that, you're actually going to have a different result. Now, having a different result means your result varies. When your result varies, then we need to be able to know the probability distribution of that result. Take a look at what I'm doing now. Expected value of P cap, we expect it to be P. What is our P? Population proportion. We expect that on average, if P cap, if this guy, look at this guy, is this guy, if they follow normal distribution, and I'm going to say that again, if this guy follow normal distribution, then the expected value of P cap will be equal to P. It means what we expect to get from the P cap will be the same as what we intended to get. What do we intend to get? We want to get the population proportion, which is the true proportion. This is what we're supposed to get when we investigate everybody in the population. But statistically speaking, okay, if P cap, if this guy follow normal distribution, I'm going to say that again. If this guy follow normal distribution, the expected value of this will be this. Which means, you know, the meaning of expected value, I should find the average of this guy. Look at that. Average of this guy. How do I find the average of this guy? Okay. So finding the, now take a look at that now. If I want to find the average of that guy, expected value, and don't forget, what is your P cap? X over N, right? Your P cap is X over N. N is a constant, right? Take a look at that. You know, it doesn't matter if I'm not able to finish this today, but I need you to understand. That's what concerns me, you know. Now we want to do what is expected value of P cap, okay? And that will be expected value into X over N. N is a constant. That will be 1 over N, expected value of X. Okay? 1 over X, expected value of X. Now, what is the 1 over N? What is the expected value of X from binomial? N, P. What happened? What do you have now? P. Therefore, we've been able to prove that the expected value of P cap would be equal to P. Is there anybody want to ask a question about how I derive? That is number 2 now. Okay? P cap become a random variable, and we just proved that the expected value of P cap equal to P. Does that make sense? Now, if the expected value of P cap equal to this, we need the variance of P cap. If you take a look at what we're doing now, the variance of P cap will be variance of X over N. Don't forget, P cap is X over N. N is a constant. If N want to come out, it's going to be 1 over N squared. Okay? When you have 1 over N squared, then the variance of X. What is the variance of X? Binomial, NPQ, right? So 1 over N squared, NPQ. This guy cancels this guy, right? If that guy cancels that guy, what do I have now? I got PQ divided by N. Another way to write this is to write P into 1 minus P divided by N. You know why? Because P plus Q equal to 1. P plus Q equal to 1. If P plus Q equal to 1, then Q is going to be 1 minus P. Now, look at the variance now. The variance of P cap now. That was how we get PQ over N. If the variance of P cap equal to what I have here, or here, what would be the standard deviation? The standard deviation of P cap is going to be the square root of the variance. The square root of the variance. Now, if I now want to impose a normal distribution now, because when something follows normal distribution, we must be able to know what does it mean, what is the variance. Does that make sense? There are 2 parameters in a normal distribution. This is the mean. This is the variance now. And that was why I said P cap follow normal distribution with the mean of P and the standard deviation of that. Any question? The standard deviation of PQ divided by N. Any question? Any question? So far, so good, right? If there's any question, please let me know. Okay. Now, but let me tell you this. What of in a situation where the population you are choosing from is not normal, then it is encouraged that you choose a large sample before the sampling distribution of P will follow normal distribution. And how large is a large? At least story. Does that make sense? Okay, now, do you know that the other time we actually standardize mean, right? We use a z-score when we want to ask probability about mean, right? We can also do a z-score where we want to find probability about p. This is what you see now. Your z-score will be p cap sample proportion minus the population proportion divided by that. What do you think we're doing here? What do you think we're doing here? What we're actually doing is this. What we're doing is z equal p cap minus the mean of the p divided by the standard deviation of p. That's what we mean. So which is going to be p cap. What is the mean of the p? This. What is the standard deviation? What we derive. That's why you have that. The formula for z has not changed. The formula for z has not changed. It is going to be a statistic minus the mean of the statistic divided by the standard deviation of the statistic. The statistic here is p cap. P cap. Does that make sense? Okay. Now, how do we do for two populations? We want to compare proportion in two populations. Let me give you an example. Let me go into, maybe I want to compare. I want to see whether if I focus on Minnesota and Illinois, okay, now if I want to compare the proportion of Americans who own guns in Minnesota and the state of Illinois, I want to see whether there's a difference between them. I'm going to say that again. You know, how does that qualify to be a proportion? Because it is not everybody in the state that owns gun. That become a proportion. So I mean, want to know what is the difference between the proportion of Americans who hold guns in the state of Illinois and in the state of Minnesota. Are they the same? I may also want to compare the proportion of women in the House of Representatives compared to the proportion of women in the House of Senate. Is there a difference between them? Does that make sense? Now, it means I'm talking about difference of proportion. Do you know that if every one of you should go into the population now, okay, let's say number one person in this class, okay, go into the US Senate and House of Representatives and take a sample. Maybe I give you question to take a sample randomly, okay, to the best of my knowledge. How many senators? US, I think it's 100, right? House of Representatives in the House, is it 430 something? Can somebody remind me? 435? Thank you. 435. And I say, okay, you know what? You know, I have two different groups, right? And I say, okay, each of you should go into the population, select 40. But it may not be equal, but your sample size has to be large. How large is a large? At least story. Now, if I ask, let's say one person to go, the person is going to get me this, right? Out of the 40, how many are women? That will be that number divided by 40. Out of the 40 here, how many are women? That number divided by 40 will give you this. Now, this is for one person. Do you know that if I have 50 people in this class, 50 students in this class, how many results of this am I going to get? 50. Don't forget, you guys are selecting them at random, which means your results will vary, right? Now, I'm going to have this guy in 50 ways, depending on the numbers of investigators. You see reason why different organizations get different results? Because they are not using the same participants. They are choosing at random. Now, if this guy now become a random variable, which means we're going to have a lot of them. then we need the mean of them. The mean is going to be called expected value. We expect that the average of that should give you this. What is this? The difference in the population one. And the variance now, why am I talking about variance? I'm talking about variance because there are so many of them. This is where you're now going to use the knowledge that you know what you've done before. Like, what is the variance of x minus y? Okay, you remember? Variance of x minus y, variance of x plus variance of y minus 2 covariance xy. Do you remember? But because they are independent, the two groups are independent, the covariance will be equal to 0. In this case now, I'm actually going to have the variance of P1 plus the variance of P2. Does that make sense? That's what I'm going to have. The covariance will be equal to 0 because the two house that I'm talking about are independent. Now, what is the variance of P1? Oh, the variance of P1 will be P1 Q1 over N1. Don't forget that the variance of P was PQ over N. Do you remember that? The only thing you're going to do is to put 1, 1, and 1 here. And here, you're going to be P2 Q2 divided by N2. Do you see that? This is going to be the variance now. What will now be the standard deviation? You're going to find the square root of that. Any question about what you see on the board? That's why you have what I'm projecting now. Take a look at that. It now means P cap 1 minus P cap 2, that is now random variable. Now follow normal distribution with the mean of P1 minus P2, okay? With the mean of P1 minus P2 and the standard deviation of that. Any question? Now, we can also calculate a z-score for that. Oh my God, if I say z-score, I mean the statistic minus the mean of the statistic divided by the standard deviation. What is the statistic in this regard? P cap 1 minus P cap 2. What is the mean of that? P1 minus P2. What is the standard deviation of that? What you see in the denominator that we just proved out right now. Any question? Statistics is very, very easy. When you relate, look at that. Look at what we've done now. We visited Congress. Very easy. Because when you try to relate, you know, what you learn mathematically, you will appreciate what you are learning. Okay, now, you know, I promised you the other time that I'm going to show you a t-table, right? There's a t-table now. Okay. Do you know the values that we have here? They were generated from t distribution. This value here. Okay, you can check the v that you see is what we call degree of freedom. If I know the values of degree of freedom and I know the level of significance alpha, I'm just going to check for the value. Okay, go ahead. Oh my goodness, that's a good question. Somebody asked, when do we know when to use a t-table? That's part of what we want to do today. But let me tell you this, we're going to use t when the population standard deviation is not given. We use z when the population standard deviation is known. I'm going to say that again. We use z when the population standard deviation is known. We use t when the population standard deviation is unknown. Have I answered your question now? Good job. Now, I'm going to go to sampling. Now, take a look at this. We've done, let me just say in statistics, we got several parameters. You know, I said parameters are whatever we want to figure out, which is what I call a population characteristic value. Do you know that parameter can be mean? We talk about mean. We talk about mean in one population. We talk about difference of means. We talk about proportion right now. We talk about difference of proportion, right? Do you know we can also talk about variance? Variance is also parameter. Imagine if I give you this work and I say, okay, you know what? Go into the university, take a sample of 50 students. If I say each of you should go into the university, take a sample of 50 students randomly, ask them how many hours on average do they spend studying a week? I'm going to say that again. Maybe I give you a question. I give you a research work. I said, you know what? Go into the University of Minnesota. Okay. Now select 50 students at random. Ask each of them. Okay. You want to know the number of hours they spend study in a week. Of course, you expect them to give you different values, right? Now, if my interest is not on mean, if my interest is on variability, then what you're going to find is to find variance, right? Now, if you find variance, this person find variance, let's say you guys are 100 here. If you are 100 in this class, how many values of variance are you going to have? 100. And that is the reason I'm equating you now to investigators. Reason why investigators work on the same research, but they get different results. Then how can we now trust? Like, what can we do for us to be able to know which one is the true? Then we need a sampling distribution of the sample variance. Does that make sense? Because the result that you got varies, right? And when it varies, it becomes a random variable. So which means before we can now say, okay, let's look at the average of the variance now. And let's look at the variance of the variance. This time around, the variance is a random variable. But before we can conclude on whether we should find the mean of the variance, because we got a lot of variance values, we need to know the distribution. We don't just find mean. Before we can find mean, the distribution has to be normal. We don't just find mean because we have more than one measures of central tendency. You know that, right? Mean, median, mode. But mean can only be trusted if the distribution is normal. Does that make sense? Now, I present to you now sampling distribution of sample variance. It's more or less like you've gone into the population now, and each of you compute variance, you get different values. Okay? And we don't want to take, a decision on that. Okay, now, if we want to find, if you take a look at what I'm trying to show you now, sigma squared is population variance, S squared is sample variance. Does that make sense? The only way you can get population variance is when you study everybody in the population. Do we do that? Do we normally do that? No, we don't have resources for that. We're only going to take a sample. But the issue with the sample is this. If different investigators go into the population, they're going to have a different value. How do we validate the result that we got? And in research, we normally go once. Do we go more than one time into population? No, we only go once. But how are we going to show the world that even though we have gone only one time, our result is going to be fantastic? It's when the central limit theorem applies. When you take a large sample. Now, we want to look at the distribution now. The distribution we want to look. When you are focusing on variance, when we are focusing on variance, we don't talk about normal distribution anymore. Okay, take a look at this. N minus 1 S squared divided by sigma squared. We want to focus on this. What is this guy? Sample variance. What is this guy? Population variance. what is this guy? Degree of freedom. Degree of freedom is the sample size minus 1. Okay. Now, and that was why I said, if a random sample of size n is drawn from a normal population with a mean mu and a variance sigma squared, okay, I said, and the sample variance is computed, we obtain a value of the statistic S squared, the value that each of you obtain, sample variance. That's what you obtain, right? Now, we shall proceed to consider the distribution of the statistic. We want to consider this distribution. You know what we're trying to do here? The ratio of sample variance to the population variance multiplied by the degree of freedom. Okay, now, if you take a look at summation xi minus mu or squared, what do you think I just introduced? What did I just introduce? If I have summation xi minus mu or squared, and I start from 1 to n, let's say I have xi minus mu. I only introduce x bar minus x bar. Have I introduced anything? Because this guy cancels that guy. But I want to use it. That is what I do here. Look at that. X bar there, x bar there. Any question? Any question? That very row? That makes sense, right? Okay, now, when you now go to the second row, of course, we are more or less doing a plus b, mathematics, all squared. What is that? A squared, b squared, plus 2ab, right? Mathematics, right? That was what led to that. Look at that. Summation x minus x bar all squared plus that. Do you see that? That is like doing mathematics now. Okay? Take a look at that. But you know what? The last entity is going to be equal to 0. More or less like a covariance. If the last entity here, you know why? I'm going to show you now. Why the last entity will be 0? You're going to see now. You know, the last entity, you have 2 into x bar, or 2 into x bar minus mu, summation I start from 1, xi minus x bar, sum of the deviation is 0. This guy here is 0. How? Let's prove that. If you multiply, that will be summation si minus summation x bar. Okay, summation xi minus summation is going to be n x bar, because this is not a variable anymore. Okay, now summation xi minus n. What is x bar? Summation xi over n. So n cancel n. What do we have? Any question? Any question? That is how the other entity becomes 0. Now, when the other entity becomes 0, look at what we have now. You know, right now, I'm going to show you. Now, right now, we are left with summation xi minus x bar squared plus summation x bar minus mu squared. I start from 1 to n. I start from 1 to n. X bar, that's a constant. Mu, that's a constant. That this guy is going to turn to n. So I'm going to have summation xi minus x bar all squared. I start from 1 to n, and x bar minus mu squared. This is what I have. Take a look at that. Now, the moment I have that now, okay, let us now divide both sides by n. Say dividing each time of the equality by sigma squared, okay, and substituting n minus 1. You know, when you take a look at this now, you know, right now, this guy, we have summation x minus mu all squared equal to this. We now said, let us divide them by sigma squared. Okay. And after dividing by sigma squared, okay, we want to substitute n minus 1 s squared for that. Okay, this will happen. How do I know? What is the formula for sample variance? Is this guy here. You know, that is the formula for sample variance, right? If I want to get this guy, what is it going to be? Right? If you solve for this guy, right? Now, if you take a look at what I have here, summation xi minus mu all squared divided by sigma squared. I start from 1 to that. Summation xi minus x bar squared divided by sigma squared plus n x bar minus mu all squared divided by sigma squared. Anywhere I see this guy, I want to put this guy. Anywhere I see this guy, I want to put this guy. Right here. It means it's going to be right here. So this guy now, I can rewrite this at 1 over sigma squared. That's what you have here. Summation si minus mu all squared. I start from 1 to n equal. What am I going to substitute here? I'm going to substitute this guy. Okay? N minus 1 s squared. N minus 1 s squared over sigma squared plus. This is going to be x bar minus mu all squared. I can rewrite this as this. I can rewrite this as this. This as this. Do you see that? Take a look at that now. So this is now equal to this plus this guy. That is what you see here. Can you see that? And we know from what you've done before. What is this guy? When I have summation, when I have x minus mu, you know, when you take a look at this guy, do you remember when I have x minus mu over sigma, you know, it is z, right? When I square it, when I square z, is going to be this one squared, right? Do you remember what we've done before? When z is a standard normal distribution, when I square that, it becomes a chi-square. If it is 1, it becomes a chi-square degree of freedom 1. But this is a summation here from 1 to n. Can somebody tell me for extra credit, what would be the degree of freedom? If this is a chi-square now, what would be the degree of freedom for this guy? You know, for this, when I square it, this one now is a chi-square of, this follow a chi-square of degree of freedom 1. If you go back to what we've done before, z1 squared is a chi-square of degree of freedom 1. If I have z1 squared plus z1 squared 2, if I have z1 squared plus z2 squared, that becomes a chi-square of degree of freedom 2. z1 squared plus z2 squared plus z3 squared become a chi-square of degree of freedom 3. This one becomes the chi-square of degree of freedom 1. And send me a message for extra credit. This is a chi-squared degree of freedom n. This is like, you know what this guy is telling you? It's like z1 squared plus z2 squared until you get to zn squared. That is what this guy is telling you. Because z is x minus mu over sigma. Any question? And that is how you have that. Now, because of that, we're basically going to say that guy follow a chi-square distribution. Okay. Now, if it follow a chi-square distribution, we are now going to say the degree of freedom, instead of n, we are now going to say it's going to follow a degree of freedom n minus 1. Why? You know, when we have n observation, what do we always do? We subtract 1, right? Okay, so that is why you have that. And This is a chi-square now. So anytime you have the ratio of a sample variance divided by the population variance multiplied by the degree of freedom, then the distribution is chi-square. I'm going to say that again. If I have the ratio of sample variance to the population variance, okay, and you are multiplied by the degree of freedom, the distribution is going to be a chi-square. Okay, and this is a chi-square shape. Now, I will walk you through an example before I go. What is the application of this? A manufacturer of car batteries guarantees that the batteries will last on average 3 years with a standard deviation of 1 year. If 5 of these batteries have lifetime of 1.9, 2.4, 3.0, 3.5, and 4.2 years, should the manufacturer still be convinced that the batteries have a standard deviation of 1 year? Because at times the manufacturer could mislead us just because they want to sell their products. And that is the reason why we need the knowledge of statistics to be able to investigate. If you really want to live this world successfully, on average, you need a mathematical knowledge. And that's why we're here. Okay, now, do you know what we now need to do? You need to calculate your S squared. Okay, your S squared in this case, if you use a theorem 8.1, that I actually put in the textbook, how many observations do I have? Okay, 5, right? Do you see 5? Okay, then for the 8.6 minus 15 squared divided by 5 times 4, you know what we're doing now? We're actually finding the sample variance. If you don't want to go by days, that's no problem. Okay, how do you get a sample variance when you have those numbers? You know what you're going to do? You want to get sample variance? You find the mean. The mean is 3, right? So if you get a sample variance, if you work the sample variance out, that's basically what you're going to have. Then you can now find the chi-squared. What are you going to use to find the chi-squared? Okay, don't forget, if you want to find the chi-squared, your chi-square is this guy. This one is the sample variance that you first compute. Your population variance, okay, is what you're going to pull here. Okay, here now I got 4, right? I got 5 minus 1. The S squared is the sample variance that I compute. Okay, then the sigma squared is 1. How do I get 1? Look at it. Convinced that the battery have a standard deviation 1 year. If the standard deviation is 1, the variance is 1. Then this guy 3.26 now become a test statistic for the chi-square. Test statistic for the chi-squared. Okay, test statistic for the chi-squared. I'm going to stop here and I'm going to continue from here. Don't forget your exam is going to be April 17. I think you know that, right? Okay, so I'm going to stop here. We'll see you on Monday. We're going to continue from where we stop. Make sure you stay safe and have a lovely day. Bye for now, everyone.